we have thermodynamics, and we are asked to show that Cp minus Cv is equals to Nr. And these are thermodynamic relations. We have a Cp, which is a constant, and we also have Cv, which is also a constant. And of course, this might be familiar because from the ideal gas equation, we can have this expression Pv, which is equals to nRT. And definitely, you'll notice that there is a bit of similarity here. If you look at the two, you notice that we have a bit of similarity. From this side, we are seeing Nr, and here we also have what? Nr. So what do you think is going to give us Nr here? That can only happen if we divide this term by T, divide this term by T. Definitely, this is going to cancel this. So we are now going to have PV over T as against what? Nr. So what does that mean? If we have to differentiate this term, that is, if we have to take differentials here, then we are going to have P dV over the T, all is equal to what? Nr. And at this point, the V over the T is 0. So if the V over the T is 0, that is to say, this expression for T will be what? 0. And this will be what equals to Nr. So what we need is P into what? The V over the T at a constant pressure. But if the temperature is kept constant, then this entire term will be what? 0. But if we have this expression, which is the same as PV, but at this point in time, our pressure is constant and not the temperature. That is one of the things that we are going to look at when we are going to derive this particular expression. So, if we are to recall, for the standard molar heat capacity at a constant pressure, that is Cp, standard molar heat capacity at a constant volume, that is Cv. These can be obtained from this graph. If we're asked to plot a graph here of the enthalpy against the temperature, and we have a straight line here as the point that we plotted, and you're asked to find the slope or the gradient, then it's going to be the change in H over change in T at a constant pressure. The change in H over the T at a constant pressure. Partial H over partial T at a constant pressure. And also, you can also have another relation here. Wherein, if you're asked to plot a graph against using the internal energy against the temperature, then the gradient will be U over T at a constant volume. So this is the gradient for this particular function, this particular graph. So this is how we can obtain the values for our Cp and what? Cv from this expression. And these are expressions that you need to know all the time, because if you are asked to obtain or show the relation that confirms this argument, because this is an argument that you need to show in a thermodynamic sense. So this is the graph where you obtain our gradient function, the H over the T at a constant pressure. Also, the same for this. If we are to plot a graph of what? The internal energy U against the temperature, and you're asked to find the gradient or the slope, it is what? The partial U over partial T. That is the internal energy over what? The change in our temperature. So, from this relation, we can now tell that our Cp